So welcome everyone. It's a pleasure to welcome you to today's Tao seminar. And it's great having here Dr. Gourihar Kulkarni from Pacific Northwest National Laboratories, giving today's seminar via Zoom. Obviously, he's on the West Coast, further away, and I'm really glad he made time to join us today. A few words to Gourihar, who I have known now, I think, more than 15 years, and a few comments on that later. But Gourihar started in mechanical engineering, so he's a trained engineer, did his bachelor degrees in mechanical engineering, Karnataka University in India, but then afterwards went to the University of Leeds in Great Britain, did his master's in computational fluid dynamics, and I now realize how he has such well-controlled experiments because he computational fluidly simulates them. And then continues to get his PhD in atmospheric sciences also at the University of Leeds. Then after 2007, roughly, he joined Pacific Northwest National Laboratory, and he quickly rose through the ranks from postdoc to now being a senior scientist, an earth scientist, leading the ice nucleation laboratory, but also not only ice nucleation, also cloud formation experiments, laboratory experiments, and also field measurements. A few words on his scientific appointment, what is maybe important here for some of the audience. He is an ARM mentor, meaning like about 50% of the time, he told me or so, he is involved with ARM data. So that means cloud condensation nuclei data, INP, ice nucleating particle data, but also general field campaign data. He is editor in the Frontiers in Environmental Science journal. What is relatively new, he's a STEM ambassador from Pacific Northwest National Laboratory. So if you have any thoughts, ideas how to teach atmospheric science in schools or which kind of experiments, I didn't know that, so I have to reach out to him. Gourihar is the person who knows most about that. So he has several outstanding performance awards. As I say, he rose very quickly through the ranks at PNNL. I know Gourihar very long. I always appreciated his very careful laboratory studies of ice nucleating particles, and now going also in the field with new instrumentation. And so I'm really looking forward what he will be telling us today. And so with not much further ado, Gourihar's talk here the title is Use of Laboratory Field Observations and Modeling Data to Study Cloud Nucleating Particles. And yeah, Gourihar, take it from here, and thank you being with us.
No, thank you. Thank you, Daniel, for this nice introduction. And really appreciate the invitation just to give a talk, give a seminar at, and good to see all of you virtually. So great. So as Daniel mentioned that about the title. So I'm going to talk about how we are using the lab data, the observations, and the modeling data to understand more about the aerosols. And so the aerosols which form the ice crystals, we call those aerosols as INP, or ice nucleating particles. And the aerosols that activate into droplet, and we call them CCM, Cloud Condensation Nuclei. So I'm going to give an overview of the work we are doing at PNNL here regarding the INP and the CCN. So I'll say something more about the ice residuals. So basically to understand more about the aerosol properties that actually are important to form an ice crystal. Then what is the budget? What is the total concentration of INPs in the atmosphere? And also something regarding something very new, this is the INP properties of engineered sea salt aerosols. And finally, I'll talk on the CCN, the data observations, and how we are calculating the budget. I should say that the first few slides are kind of introduction, and you might have seen them many times. but actually they help to set in a stage for the presentation. So the question is, why want to study aerosols in the cloud? Before that, you must have seen this figure many times. Is the Earth is warming. Here is a data from last 130 years or so, shows very clearly that there's a trend in the warming. So this is the x-axis is the time, the y-axis is the global surface temperature. So this is the surface temperature. How about if you look at the in the atmosphere? Sorry, in the atmosphere itself, like in situ. And we see the same kind of trend that the Earth is warming. The temperatures are going up, and you can see from the satellites and the heat uptake to the data, it's very clear. So what's happening is if we go down to this particular slide here, is there are two different components which plays a role in energy balance. So the components that are kind of telling us like greenhouse gases and short-lived gases and black carbon and other some gases, basically, they are contributing to the warming. Okay, so if you look at the components on the right side of this dashed line, those are all basically are contributing to the warming. So, but other side, there are the aerosols and the clouds, which are playing a key role in trying to cool the planet. And there is a delicate balance here. This is like a tug of war. And so it has to be in equilibrium. If you're moving towards one side, you might cause warming. If you go on the other side, you might cause cooling. And so it's critical to have this balance. So far, if you look at our scientific understanding, we have pretty much good understanding about the greenhouse gases and the short-lived gases, other greenhouse gases, ozone, for example, but we don't have a very good understanding of clouds and aerosols. What are the aerosol properties? What are the properties of the clouds? How the aerosols and the clouds interact? And so basically, we're trying to understand more about this particular part, clouds and aerosols, so we can understand more about this, delicate balance. So another takeaway. So this is from the IPCC showing that in future, what would happen to the cloud? So right here, what they say is in the future, the clouds may form at higher altitude. So what that means is that you have very less energy transmitted into the atmosphere or in the space itself. So basically, there's more warming. You're trapping more heat. Then the next one, they said that in the future, there will be fewer clouds. So if you look at the volume of the cloud, the mass of the cloud will be smaller. So what that means is they're going to trap more heat rather than reflecting back into the space. Also, they mentioned that it could be the composition could be different. So what composition means is every cloud has the water droplets and the ice crystals. And so the number of those droplets and ice crystals could increase and they will shrink in the size. And that has some different effects on the energy balance. So going back again, some basics here, you can't form a cloud or a droplets without aerosol particles. So the aerosol particles are lifted up, they take the water vapor, and you have this cloud droplets. And when you have the millions and trillions of droplets, you have in a cloud. So you need to have the aerosols to form a cloud, but the aerosols are not really uniformly distributed across the globe. So here's a simulation that shows how the different aerosols are distributed across the globe. So what you see here is the whitish color here is all the smoke, biomass burning. The bluish is the sea salt, and there's a dust coming from the desert. And what you can see, it's not really in a patch where you only find dust or sea salt or the biomass burning, smoke particles, but they kind of, mixed in the atmosphere. So that makes our life extremely difficult to understand, how these aerosols are affecting the cloud. Yeah. Now, did little, is to understand more about the individual aerosol particles, how they look. As an example, like for example, this one is a dust. Here is an example showing the dust is coated with organics. It is also sulfate. There's some biological particles you can see. There are the dust particles, and there's a biological particles attached to it, and some other different morphological particles you'll see. You can also see, if you look at the Raman spectroscopy, if you take a look at it, you can see that the interior core is different than the shell. If you look at the ice residuals or droplet residuals, they look very different. So the key message here is the aerosols are complex. If you want to calculate the surface area, it's very complex. If you understand more about the properties, it's also very difficult. And so the big question then is how these particles actually interact with the clouds, and how you can understand this aerosol cloud interaction. So here's another way to look at it. So basically you have different sources of aerosols, lifting up. For example, the sea spray from ocean, dust from the desert, organics and biological particles from the forest, and of course you have the um, soot type particles from the anthropogenic emissions. So all these particles are mixed together. They form cloud droplets. We call this low-level clouds. And when these droplets are lifted up below the freezing level, these droplets start forming the ice crystals. So the question then is, and we have seen this many times in the lab, is if you have 100 aerosols, only 20% or 40% aerosols form actually the ice crystals, or they have the droplet into they activate into droplets. The question is why. So let's dig into more on the ice clouds. So you have 4 different or maybe 5 different ice nucleation mechanisms. These droplets could lift it up and they will freeze only below -38. Basically, we call this homogeneous freezing. These are basically pure organic solution droplets. All the acid, it's a pure solution droplets basically. So there's another mechanism called deposition or the pore condensation. That's another way of looking at it, is basically how the aerosol particles, the water vapor directly condenses on it, and you have an ice crystal. The immersion mode is where you have a liquid droplet, and inside there is your aerosol particle, and the aerosol particles, leads to the formation of an ice embryo, and you have an ice crystal. And the contact freezing is where you have supercooled droplet, and these aerosols come in contact, exterior or from inside, and you get an ice crystal. So it's very complex to even to study the ice clouds. So I'm getting into the lab now here. So in the lab, we have the ice nucleation chamber to study the how aerosol particles could form an ice crystal and under what conditions. So this is the custom-made available in the lab. You can also apply in the field. It's a fully automated. It's you can have the custom scans. That means you can increase the temperature, decrease the temperature at the rate you want. It samples approximately. It's a very high statistics. It's like 1 million droplets per minute. It's really high. You get the statistics on the droplet freezing spectra. Different INP modes. You can go from -5 to -60 degrees C. You can explore deposition, immersion, and homogeneous freezing modes. And typically, we have used this instrument to get the frozen fraction, the INP concentration data. We've recently started looking at the ice residual, and my talk would be more on the ice residual part, which is the kind of understand more about the specifics of the aerosols that led to the formation of the ice crystal. We also done a lot of aerosol aging. We connected that to the other upstream and downstream instruments to look into the different the properties of the aerosol. So this is the kind of an cross section of the chamber. So the aerosols come from the top, then they are activated into the droplet. So basically, they are supercooled droplets. And then what happens is these droplets are exposed to the some certain temperature, and you form an ice crystals. And all this, the unfrozen supercooled droplets are evaporated. they're taken away. So basically at the end of the chamber, you're left with either the ice crystals or the unactivated particles. And then what we do is using the instrument called PCVI, we separate those. So basically at the end of the chamber, we have the ice crystals and the interstitial aerosols, the aerosols that did not form the ice crystal. So then what you do is we separate those, the ice crystals from the interstitial. And then once we have these ice crystals separated, we crack open those ice crystals and look at the what is so special about those aerosol particles. They nucleate the ice. And here is and again the cross section showing you the what happens within the PCVI. Basically, there's a flow coming up, and there is a two stagnation planes. Basically, there's a flow against the main inlet flow, rejecting the particles, of smaller size. So basically, larger size particles are collected in the output. So our first deployment was in the Stomping lab. Stomping lab is in Colorado State. It's approximately 10,500 feet height elevation. And it's very ideal to sample the continental background aerosols. And so we are doing this sampling in the middle of the night in the winter time, and hoping that the site will be in the free troposphere, and they will sample the air mass coming from the long distances. We are hoping to get some dust from the Asia. That was the idea. So here's the data from this particular campaign. This is ice residual data, by the way. So this is the background aerosol composition, how it looks. The majority is the organics and biomass burning. But if you look at the INP composition, you can see the pie chart colors are different now. And so you see over here that although dust is a very tiny fraction in the total aerosol, but in the INP, it's a dominating. And what is telling us that that dust is a very important component of the system here. So what is this telling us? That from all the study, just summarizing, is telling that aerosol composition is important for INP or ice nucleation. Here's another experiment we did in the lab. So this is data showing the immersion freezing data for the dust, particularly ATD, which is used kind of in a surrogate for a dust in the lab work. And you can see, so there's a plus marks of the ATD here. It's all over the place. So -20 to all the way to -40, and they have the different efficiency values too, which is represented by NS. So we said, well, dust is commercially available, this ATD. What is so special? So we did the ice residual work on this. So here is the data again. So this is the dust, just what you're putting into the chamber. So the x-axis is the size, and the y-axis is just the normalizer frequency. So we had like 100 nanometer particles selected, 200 nanometer particles selected. You can see this multiple charge and then triplets too. We see sometimes for the 100 nanometer. So broad range of sizes we are putting into the chamber. And now what is interesting thing is that when you look at the composition of it, that's the key part. This composition is very similar for the total aerosol and the ice residual, but what we see is the lead, it's always peaks off. So the ice crystals, which we looked into, they always have the lead in it. So what is it telling us here is that the both size and composition is important, but not only size or composition, but both are important for this ATD kind of aerosol. So here's another experiment we did with the volcanic ash. So we collected the ash from the Iceland volcano 2010, and we looked at it. So here is the thing. So here is the blue trace shows what we're putting into the chamber, and this particular one trace here, colored one, shows the ice residual. So what it's telling us, the size plays a huge role here, but there's no change in the composition. So the composition of the total aerosol is very similar to the composition of the ice residual. So in this particular case, the size, the only one matters in this ash. Then we looked at another one. Here's the interesting one was we had the soot generator in the lab, and we generated the diesel soot, and we looked at it. So what we see here is that at minus 20 degrees C supercooled droplet, the soot is compacted by something like this, whereas at the minus 40 degrees C, instead of minus 45 degrees C, soot is highly compacted. And that's what we started with. That's a fractal soot we started with. And what it's telling us in this particular experiment is size plays a role, but not really the composition has anything to do with it. Here's another experiment we did here. We had the two ice chambers, and we connected in the series. So the ice residuals from one chamber were sent to the to other chamber to understand more about what happens. Although I should say that it's a funny story that this paper got rejected for like 3-4 times. It's just the reviewer didn't understand. But finally went through it when they understood what is exactly is going on. But what's it telling here is that, so this data here is the frozen fraction for the first chamber. And this data here, the field squares, are the data from the second chamber. And what you see here is the comment the reviewers was main thing was that you should get 100% activation the second time because they've already been activated once. And what we see is they don't. So I repeated this so many times this experiment, it does not. And what is it telling us that there has to be some dependence on size composition, but also the cloud processing also plays a role in this. Just to summarize these studies and other studies we have done, and what we think it is for some aerosol, size matters, for some composition matters. And the hypothesis what's emerging is that the composition matters for complex mixing state particles. So if the particle is a complex, it has like sulfates and organics and other things, then composition matters. Whereas if the composition is simple, size plays a huge role. So that's kind of the conclusion from this ice residual work we have done in the PNL. Now, so moving on to some other area where we're trying to calculate now the budget of this INP, ice nucleating particles. And so, so what we did was, so we had the high scale campaign in 2016 at the SGP site. This is the ARM site. And so we have the aircraft flying. Let me see if you can. This one. Okay, here it is. Yeah, so when the aircraft was flying, we are collecting the aerosol concentration data. We are also collecting the CCN number concentration, which can show over here. And so the whole idea here is to understand more about the vertical profiles of the composition, vertical profiles of the CCN, and other aerosol properties too. And what you're doing here is we're trying to understand. Well, let me stop this. So here's some data from this particular day. Here is the flight trajectory. Here's the number concentration for the CCN and the total aerosol concentration. Here's the site distribution data. And here is the altitude and the PVL height, some other details like a relative humidity, which was between 25% to like 70%. The temperature was between 10 and 25 degrees C. So we have a lot of data. And so what we did this is we used the particular SPLAT data, which is the single particle aerosol composition data. And so what you see here is on the x-axis is the time, the y-axis is the fraction of particles, and the legends are over here. And on this particular day, it's the particles were dominated by the biomass burning or the biomass burning SOI, like approximately 58%. And then there's a fresh organic particles and some others, nitrates and sulfates and the dust and soot. So what we did with then is, so we went into the lab. Okay, same thing. This is the films data. So we went into the lab and we generated the SOI, biomass burning surrogate SOI, I call acetone. And so basically we have the SOI chamber, we injected the VOCs, and we make these in SOI. And so we also looked into at Enzo, how they look, the morphology. Initially when I looked at the first time, I saw it like a soot, but they're not. So we had this the SOAs, and then what we did was we transported this SOA to the ice chamber to look at the frozen fraction or the activated fraction properties. See, yeah. So here is the potential INP concentration. So we have the activated fraction from the lab. We have the fraction of BBOA from the splat, which is like 58%. And we also have the total aerosols from the FIMS and other instruments on board the plane. So we can calculate the potential INP concentration or potential INP budget at the site for this particular day, which goes between like a 5 to 15 per liter. So imagine, it's like, we talk about the 1 in million particle form an ice crystal. This is an example here showing us that, the INP budget is extremely small. And so it's so important to understand it. Just quickly going to the other type of SOA, which basically alpha pinene here. So SOA phase state is very important, the global atmosphere, just because if you look at this, the plot here, at higher altitudes, these SOAs are kind of in a glassy, it's solid. That means they could potentially form an ice crystal and could affect the cirrus cloud. Whereas if you look at the surface, they're kind of a liquid. So we are trying to understand, okay, what is the INP budget of these SOA particles in the atmosphere? So again, we did this in SOA chamber type experiments where we injected the alpha pinene, which is in an abundant monoterpene. It's a biogenic VOC. And we get this alpha pinene SOA, and these SOA particles were injected into the chamber to understand about their activated fraction. So we also did a lot of other experiments to understand the cloud processing part of it. So we had an untreated, that means the SOA coming from the chamber directly transported to the ice chamber. We are pre-cooled. We also then treated because to understand more about the cloud processing. So you make them droplet, you make an ice crystal, and get rid of the ice. You sublimate it, and you're left with the modified, the organic aerosol. And what we see here is the SOA which has been treated like cloud process has a higher efficiency compared to the untreated or which is unprocessed one. So we have this data now. So we combined this data with the modeling work done by Manish Srivatsava. He did the modeling using the WARFCam or the Brazil. There's a campaign called Go Amazon by DOE. And so what he has done is he had done a lot of simulations, understanding more about the vertical profiles of this monoterpenes and other VOC, the gases. And what he sees is that for approximately 67% of the time, it's dominated by the terpene SOA, basically the alpha pinene. So here is a vertical profile of that, of the concentration. So basically the x-axis is the terpene concentration, and the y-axis is your height. So what I've done then is, so I know what is the concentration of the SOA. I know the lab data, and then I can do this calculation. It's very simple, is the multiply this to activated fraction coming from the lab, and the WARFCam simulated monoterpene vertical concentration, and you can get the potential INP budget or the Amazon. And what we see here is the numbers are extremely low. So we go to like a 5 per liter is the max at like minus 50 degrees. So the idea here is, again, to understand more about how the cirrus cloud could form. To understand more cirrus cloud, you need to understand what is the INP budget is. So this particular slide tells about what would be the INP budget or the Amazon. So again, we did some work with the engineer CSOL. So this is the small effort going on to analyze of the marine cloud brightening related work. So there are so many different climate intervention methods are there. One thing we are particularly interested in was MCB. Basically, the idea is that you inject this cloud, the base of the cloud, with the CSOL particles, and you have a numerous liquid droplets, and the idea is that they will help to reflect the sunlight back to the space. And so for that, well, here's another introduction. Again, that one, I think I'll skip this for time being. So we collaborated with the people from University of Washington, a company Park located in California, and we borrowed one nozzle, which this nozzle sits in one of the nozzle in this bank, and this goes on the top of the ship. Basically, the idea is to make the sea salt particle plume. And under certain conditions, this plume might get lifted up, and you see the base of the cloud, increasing the reflectivity. That's the idea. So we had one nozzle from them, and so then we had a setup to understand more other things. I'm not going to talk about those other results, but here's a small setup. Here's a nozzle. We have a small chamber, cloud chamber, we call it, or droplet chamber. And we inject that into the chamber. We get a lot of droplets, and then the droplets get evaporated, and you're left with the residues particles, and those residues then are transported to the ice chamber. So here's the data. Here's the result. So what we see here is that those engineered sea salt particles are not really efficient in forming the ice crystals at warmer temperature, in particular immersion freezing mode. We just don't see it. And there's another work, basically I'm comparing with that's Dan's work published in Nature Geoscience, is, that shows very clearly that the sea salt containing, or these droplets basically freeze efficiently at warmer temperature. And what we're thinking is this may be because of the biogenic fragments. The micro layer has a lot of those details which might be missing in our study here, compared to over here, which are collected over the Arctic and Atlantic Ocean, which are kind of at the surface. So okay, so moving on to the CCN now. So first question is, what is the CCN closure? Is what properties we should use in modeling to study more about the CCN. So again, I'm using the data from the high scale campaign you just saw. And so we have the CCN concentration. We also have the aerosol concentration, and we have a lot of other composition information too. So here what we did was we had the CCN measurements coming from the aircraft. And then we also had the supersaturation. And so we did some assumptions about the particles. So we did 3 assumptions. One, all the particles are organics. Second, the particles are internal mixed in certain proportion. That's given by the AMS data. And we also did assumption is making sure that they are external mixed. So all the assumptions went into it. We used the Kappa-Color theory, and using the FIMS data, which is using the site distribution information, we calculate the CCN, and we calculate. So we compared this calculated CCN to the CCN that's measured, called the CCN closure. And also we did a lot of other permutations with the changing the density of the organic particles, changing the insolubility, meaning that some of the organics might be insoluble, like in a kappa 0, they don't really activate. And here's the summary slide again. So what we see here is that the kappa value between like a 0.08 to 0.18 with the mean of like a 0.12 could represent the hygroscopicity of the organic particles which you are see in the HGP site, which actually helps in a way in the modeling. And we did a lot of other cases, as I mentioned, external mixed, internal mixed. They didn't really yield a good closure. And it tells that at first order, you can assume that the aerosol particles are pure organics with the kappa of like a 0.12, and you can calculate the CCN. So here's another well, from the same paper, basically, is showing you the past CCN closure studies. So you can see that if you look at the cities or the regions where you have an anthropogenic influence, you need a size-dependent assumption to get the good closure. But if you go to some other area where it's something like this here, where it's kind of not been influenced by anthropogenic, just having a single component or the internal mixed would be sufficient. So this is for what so far has been done. This actually helps to understand, okay, next time you want to go to the field campaign, where you want to go. So you can look at the location where you want to go and see that, where to do this season closure kind of studies. At the same time, I also want to point out that for the INP, so far, I think the Dan is the only one who has done the work at HGP site here, at the closure, but we are missing the something season closure kind of work for the INP. We just don't have that information. And I think something I would like to strongly suggest that in the community that we should go to different locations and do this, INP closure kind of, studies. Okay, so getting the season budget, this is my coming to the end. So this is again the HGP site. It's a layer of shallow cumulus. And one of the big uncertainty is that what is the season budget at the base of the cloud? And so we can't fly the aircraft every day, which is not possible. But on the ground, we have some instruments which can be used to understand what would be the season budget. And the reason you also want to understand this budget is because that somehow controls the droplet number concentration. And then that somehow controls also the INP concentration, because these droplets get lifted up in a deep convective cloud system, and you have this ice crystal. So it's kind of linked to one another. So how we're doing this is, so we have the aircraft data from the high school campaign, and the ground data, we have the Raman LiDAR extinction. So we combine this data, and as a function of co-location distance, so the distance you're away from the HGP site, then we also have different methods to look at the sensitivity of each method to calculate the season budget. And then we do the comparison and trying to find the correlation, basically. And so what we see here is that so here's the time on the x-axis, y-axis the season concentration. The black dots are the aircraft data, and here are the different methods. So RN season VAP is the ARM VAP. It's a value-added product available for the users to get the vertical season budget. That's performs really well. Whereas the Ansman method doesn't do a really good job. Leonard is another method that is also pretty good. But the Patel doesn't do any good job at all. So if you put together for like 20 plus days, and if you compare against each other, so you have the season observed at the bottom x-axis, and the y-axis is that's predicted season by this particular method. And these two lines shows the plus minus 75% bounds, basically. And the dashed black line is 1:1. And what you can see here is that this particular method does well. This also actually does well too. This is a fit. The Leonard method also does well. We don't see really good, correlation with the Ansman method. And what is telling us that, you can calculate the season budget within plus minus 75% using one of these methods, which is really good. And we also found some sensitivity to the collection distance. As you're close to the site, it's better. If you go further away, the correlation is weak. We see that too. All right, so going to my final slide, summary slide. So what we're seeing here in ice nucleation is the size and composition matters. It looks like the composition matters when the particle is a complex mixing state. For example, if you collect the particles, ambient particles, it has the sulfates and organics, then it does matter that your mixing state is important. We can calculate the vertical INP budget using the very specific lab experiments, using the field data and the modeling studies. Of course, the one thing is missing, as I said, is we don't have this INP closure kind of studies at various locations. Our studies with the engineered sea salt particles, it looks like they are not very efficient to form an ice crystal. we haven't done any composition analysis, but it looks like there is no biological fragments that actually helps to make them efficient INP. And for the CCN, at HGP side, when we did this closure study, we see that in the cap of like a 0.12, and assuming that all the particles are organics, would help to, at first order at least, to help to model the CCN. And finally, the vertical CCN budget is still challenging. We haven't really figured it out. It's still there's a lot of plus minus 75% uncertainty. We're not there yet, but I think in the future, as we have more instruments and more observations, I think that will help to understand to constrain the budget. With that, I'll stop here and I'll take any questions. Thank you.
All right, thank you, Gourihar, for this really nice overview. There's a lot of stuff: lab, field, CCN, INP. So I hope we have time for some questions.
Sure, yeah.
Please, folks, raise your hands or put something. I'm monitoring the chat too, so the floor is open. Let's give it a minute. And question, yeah. Here's a question from Steve Schwartz, who sits close to me.
Sure.
Yeah, hi.
Hi, Steve.
A lot of materials, Daniel said. You started off the talk nicely with an overview of the importance of clouds and aerosols to the Earth radiation budget and how we really have to understand that to get closure on that budget and changes. And then you went into a lot of microphysics and chemistry and the like. And my question is to you,
yeah,
asked of me a lot of times too, so I want to get your take on it. How do we connect these important laboratory and field measurements to answering the question of what's the aerosol forcing and Earth radiation budget? That's I'd like to get your take on it.
Sure. No, that's a really good question. So this is something we are also working on. So we have the big emphasis on the measurements to model. So this basically falls in that category really well. So what you're trying to get here is that maybe I should take back a few slides and show an example, simple example of the INP. Let's go back here. Yeah, for example, this one. So first thing is what you're doing is you do the observations and look at what sort of aerosol particles you might see or what you see. And then you come to the lab and you're trying to understand more about the aerosol properties. And then we take an example like here now is we have active diffraction, that's the lab data. Then you combine that with the WRF-Chem, basically that's the modeled concentration. And so you come up with the potential INP. And then what you're doing is we're taking this further into the model, and that's where the parameterization comes into play. And we're trying to understand, okay, if these are the aerosols, then what could be my INP concentration using this particular relationship or this particular data. And so once we have that, then we have this parcel kind of models. I'm not a modeling expert, but we do collaborate with the people who do the cloud parcel type, simple box model type, and they take this information, understand about the how the clouds would evolve as a function of changing this INP concentration or the CCN concentration, a simple box model. And the simple box model is being kind of constrained by the observation at one of the site, for example, HGP, where we have the data from last decades or 2 decades. So we have the constrained box model, we have the constrained, we are putting into the INP concentration or the CCN concentration, which we know. And then we're trying to understand in a simple way, what would be the radiative balance. That's just in a simple box model. And then we also have the people who do the regional modeling or the global modeling. And that's where I think one of the work we're doing in the CCN, we haven't done the INP, but let me go back there, is this particular work is, so going from the reason, the rationale behind a 3 kilometer or 81 kilometer was the grid cell. So you're going from a simple box model to regional scale model and trying to understand the sensitivity of these different inputs you put into the model. And after like we understood that 81 kilometer scale, then the idea would be, go to the globally with different, grid cells and take a look at it. But at the moment, we are kind of into the process level understanding where how do you parameterize these simple aerosol cloud interaction processes, and then do the sensitivity studies using these box models and the regional scale models to understand more about the radiative forcing. Hope that answers. Of course, I don't have an example to show that complete pipeline going from the lab to the modeling, but that's the idea is that again here as I showed as a co-location distance, we're trying to understand if you go further away or if you average the properties across one grid, what would happen. It's an attempt to understand more about this.
Thank you.
All right.
Dave.
Xian Wang has his hands up. Please go ahead.
Okay, the Gourihar, nice to see you. Thanks for giving a great talk.
Thanks.
Yeah. Now, I've been using PodDemos data or working with him a lot. So during the past field campaign, right, I want to get you some take on perspective in the future of IN measurements. So there are a few things, right? We always trouble. One is a big aerosol, right? So always with inlets, you couldn't collect a big aerosol. So anything, right? So any better way to have increased sample volume to get a big aerosol, that is one. Another is dealing with the residuals.
Yeah.
So residual one time is that you have one ice nuclei, sometimes you got a multiple residual, right? So that means, you study residual not 100%, but because now the complicated process, droplets collecting aerosol, right? So how to untangle, right? Try to answer which aerosol, which really do nuclei, right? So where to go from here?
Now that's a really good question. So let me attempt to the second question first is the ice residual. So I didn't go mention the many details, but let me see if I can, just give me a second. There we go. So if I go back to my first few slides, sorry, take a minute. The aerosols are very complex. They different from shapes, different sizes, and the let me go this is better. Yeah, this one. So we use the PCVI, as I mentioned, and you can see at the end of the well, this PCVI actually basically sits at the base of the ice chamber. And what the idea here is that, again, is you're separating the ice crystals from the interstitial aerosols that did not form the ice crystals. But note that the ice crystals, if you crack them open, and if you look at the residue, they're not really uniformly, the composition is not uniform. It depends on what you put in, basically, to begin with. So if you have the ambient particles coming in, these residuals are very complex. And so going down to, sorry, I have to go back up here now. This is the main thing. Sometimes the aerosols are kind of, the composition is very simple, like this, dust. Whereas if you look at the ambient particle collected, they're not simple as looks here. So sometimes you have these organics coming in, like coming down to your questions now, is basically, you have these organic particles. Sometimes you have only the dust particles, and sometimes you have the mixture of everything coming in. What we do here is we also control the temperature. So we know which is more efficient as a function of temperature. For example, we know the dust is more efficient than organics. And so what we do is we do an experiment like a minus 20 degrees C. We do only the dust. The ice residuals are dominated by the dust particle. But if you do an experiment like minus 40 or minus 50, then it's dominated by the organics. And so with that, what would happen is we would understand what is so special about these dust particles or special about the organic particles. So that's one way of looking at it, is to you basically control the experiment in a way, you control the temperature in a way that there's more efficient particles will form the ice crystals, but not others. Whereas if you go for organics kind of thing, then you have those particles which did not form ice at the dust temperature would form the ice crystals there. So basically you control the temperature to understand more specific about the composition of the ice residuals. That's a trick we play in the lab all the time. So then the question is why we do this ice residual work. The main reason behind this is to develop the parameterization such a way that those parameterizations kind of that composition is added into the parameterization. If you look at the real world ambient particles, they're very complex. And it's very difficult to parameterize this kind of this process or these properties. So the ice crystal residue analysis tells us that, okay, you want to focus more on only on this, this, and this, not others. And that actually helps to develop the parameterization. We haven't done that kind of work, but the motivation behind all this doing this work is that you have those control parameterization now to put into the model. And coming to your first question about the volume sampling, that's something we struggle a lot. In fact, this particular chamber has only a sample volume of 1 liter per minute. We are not sampling a lot. It is a limitation of the chamber. If you're doing an aircraft, then of course, we are not sampling like thousands of liters per minute. I think that's also a limitation. But in the future, I think we should be looking into this, how we can sample this in large volume and understand more about it. But you're right that these results are kind of constrained by the sampling volume at this point. But we do have other way of means of, like, for example, we have the filters that we collect at like 200 liters to 500 liters per minute. And the filters are then taken to the lab, and then we take off the mass which is accumulated in the filter and look into the composition of it. We look at the the INP from that too. But they're not like real time like this chamber and the aircraft is. So there's like caveats plus minus here. So
maybe I can comment also on Jen's very good question, the first one. It is really a problem in the community. It's recognized. We have to sample coarse mode particles very well and their composition to understand ice nucleation. Because size matters often, as Gourihar showed, and it's really a challenge to sample in an aerosol coarse mode insufficient numbers, but also the composition. That is one of the key questions we have. And that needs also instrument development, inlet development to do so. And that also is a question I had for Gourihar. Some of your potential INP curves or derivations you mentioned there in the subscript. This was mostly for small particles, so for 300 to 500 nanometers, what we can measure on the aircraft.
Right.
So in principle, your relationship here would only hold for this kind of size range, or?
Yeah, that is true. Basically, we're kind of limited in terms of the size here. I should also mention that recently there was a campaign took place HGP side where there was an effort to sample the larger size particles and take a look at the frozen fraction, also the ice residual analysis. I think hopefully very soon that paper will be published. So or submitted, I would say. And I think you'll have more details on it. So there's some work has been done there on that aspect, but little though, not much. So.
One second, there's something in the chat. What is this? Each year for ice nucleation, under what circumstances, for what type of aerosols can size matter more than composition? So for which particle type classes do you think size is more important than composition? And then each year would like if you could elaborate or explain once more this potential INP idea. So first,
Sure. Yeah, so what you're seeing in the lab is the size matters a lot if, for example, like a dust. And the dust has its only silica and other those minerals, but nothing to do with the other things, like, for example, the organics or the sulfates. So if you have a system something like that, simple as that, then the size plays a huge role. The best example I've shown is the volcanic ash. We just don't see any composition dependency there. We did experiments with a lot of different sizes, 100 nanometer till 500 nanometer, but we just don't see any composition different of the ice residuals compared to the total aerosol. It's only the size all the time. Whereas if you do something like an ATD, which is kind of, which is dust, but also has other impurities like lead. And anytime we see that impurity, it's the composition. So what is telling us that even the small impurities plays a huge role. And we did the work, we haven't shown the work here with the soils. We did a lot of work with the soils, and we see the same signature is the composition does matter because if you look at the soils, they have not only dust, but there's so many other things out there, like biological fragments are there. There's a lot of organics there, the sulfates there too. And so if the system is simple, size matters, and size is the important. But if the system is complex, the aerosols are complex, then the composition plays a huge role in that too. And so the idea behind this ice residual work is to understand where is that line you can draw, because that will simplify the parameterization work. So they can then basically, if you come up with the conclusion like what the CCN community came from last 15 years, size matters. If you look at this, the science paper published in 2006 or 7, that was a long time ago. Something like that can be done for the INP too. But we need to know what is it. So coming to the second question about the potential INP, it's basically if you have in aerosol concentration some numbers, for example, let's say 1,000 per cc, then the question we're asking is, out of those 1,000 per cc particles, how many could form an ice nuclei, or how many could form an ice crystal? So that's where the potential INP budget numbers are coming from. So to do that, what we do is we combine the lab data, which is the activated fraction, then use the observation data to know the total number of aerosol concentration, and then we know the composition of those aerosols. So we combine all this information to get the potential INP. We call this potential because this is not done at the temperature where they're supposed to nucleate ice. So then at the tropospheric, basically lower level, first 1 or 2 kilometers, at that those altitudes, basically the temperatures are not really 0 degrees and below. So that's the idea. We call it the potential INP, but not really the INP budget. Hope that helps.
All right, we are nearing our time. Is there anyone more who wants to pose a question? One last quick question. Looks not. Okay, then let's thank Gourihar again for this really nice overview talk about all these different kind of measurements. And I encourage the graduate students, please stay on the call. You can have a chat with Gourihar about science, about national lab work, careers, all kind of other things. So please stay on the call, and I will hand the co-hosting then to Gourihar. All right. Thank you again, GK.
Thanks, Daniel. I appreciate it.